1, 2, 3. Do you hear me well? How's it going? How's the conference going? Did you learn something new, or have you ever, did you have a chance to learn something new? Just raise your hand. Okay, great. That's amazing. So, I hope today you will learn something new as well, during this presentation especially. And today I'm going to talk about RSocket, which is a future application protocol, which we are building at my company, actually. So, in order to not boring you with some basic stuff about RSocket, I'm going to show you how you can build a multiplayer Pac-Man game using RSocket. And during this presentation, I'm going to compare why, for example, RSocket is better than, for example, different protocols that currently exist on the development market. So, in order to save your time, in order to make this presentation as much as useful and knowledgeable to you, I'm going to share for whom this talk. And basically, if you're doing microservices, how many of you are doing microservices today? Just raise your hand. I'll try to see you. Great, a few hands. Almost all in the audience are doing microservices. That's great. So if you're doing microservices, this will be useful for you. In case you're looking for better performance, in case your HTTP is pure shit, this presentation is for you. And finally, if you're a reactive guy or reactive adopter, how many of you are using, for example, reactive programming on the daily basis or heard about that? Just a few hands. OK, I see. Have you ever heard about Project Reactor? OK, great, few people. So this talk also will be really useful for you. During this presentation, I'm going to use lots of Reactor code, lots of Spring. So I assume that you have a little bit of knowledge about Spring Framework and Project Reactor or RxJava at least. So you will understand what's going on. I'm not going into details of particular technology, but you'll just see the code. So prepare to that. All right, if you're still with me, my name is Oleh. I'm from Ukraine, from Kyiv. I work for Netify. I'm a Reactive geek. I love everything Reactive and related to Reactive. I'm a contributor to Project Reactor and I'm kind of core team of Project RSocket. So also I wrote a book recently about reactive programming in Spring and trying to organize some conference in Kyiv. So our agenda for today. We're going to start with defining the problem. Basically, what we are going to have in our multiplayer Pac-Man game, that will be the first part. Then we are going to understand what protocols do we need and then start comparing them. And finally, we'll have fun, because this is important to enjoy the presentation. So afterwards, we're going to play some Pac-Man game online in real time. And afterwards, we will finally define what is the best protocol. So let's start and let's talk a little bit about our requirements. So since we are going to build browser game, because this is the most simplest way to share an access to game with everyone, so we are going to have, as for every browser game, a server. And this server will be, during the first connection, will return us a first HTML page. But since we are doing modern application, we just want to return the HTML page as soon as possible, without any kind of delay in that, because we can put everything in one HTML page, of course, and make it really huge. But we want to make it as light as possible. That's why we're going to have some asynchronous data pushing, like server-side push, in order to send asynchronously some tiles, additional scripts, etc., and so forth and so on. Afterwards, as any kind of application, multiplayer game, we want to log into it, and then get an access to the state of the game, let the server generate the position for us, and in that way, we're going to understand what's going on in the game, inside the map. Of course, in order to show the movement, to make this game interactive, we're going to share some location with other players. This is the simplest way to, for example, to share the location is to send my position on every movement. So we're going to do the simplest way, and of course, we will be listening to updates from the server, from other players, in order to understand what's going on their side and make this game real time, right? Because we want to have some real-time game. And as a Pac-Man, you want to collect some items, of course, and as a ghost, you'll be trying to catch me. That's why, since we have some challenge here, we are going to have some scoreboard, and we will be listening to some updates for score, for who has eaten whom, etc. And we will have some interaction with other players in that way. All right. It seems that this is only about game development, but today I'm going to show you how we can use everything composed with microservices world, and we will introduce to our plain multiplayer game a little bit of bloody enterprise. So we are going to have some machine learning pipe. We will have some Kafka to which we are going to send events about players' location, about their kind of behaviors in order to build some bots afterwards based on kind of users' behaviors. And of course, Kafka, how many of you have heard about Kafka? Okay, all attendees, that's great. So usually Kafka could be considered as Elasticsearch, not Elasticsearch, but Elastic Storage. We can scale it really well, and that's important. That's why we probably won't care about that. But after the Kafka, we will have some processing pipeline, the first stage of which we will do some preparation of the data, we will do some aggregation, of course, and finally we will send everything to some metric service which will do some analysis. And of course it can do it really fast, but it can do it really slow, of course, because this is real environment, this is real machines, and we don't know what could happen, and we should expect everything. That's why, to summarize what I said, in general, in play game, we will have a few communication models that we are going to define and to build, which is server-side push, which is plain request response, which you're doing on a daily basis by sending some request from the browser and listening for response. And of course, we will have some client-side streaming, because we will stream in some location to the game server, and we will be listening to some updates from the server side. So it will be server-side streaming. Along with that, as I mentioned, we will have machine learning pipeline, which should just work because it can work really fast or it can work really slow. It depends on what's going on inside it or which data is in the data set right now. So in general, what's important for this pipeline is that it should just work. And that's it. And it should just work stably. And that's, I guess, the most important for our game because we want to build some really intensive and cool kind of bot educations pipe. So let's talk a little bit about toolkit, the main toolkit that we are going to use on our server side. On the backend, we are going to use Spring Framework 5 because this is the newest guy. Then we are going to use Project Reactor because, of course, nothing could happen without reactive programming. And we are going to use Protocol Buffer. Have you ever heard about Protocol Buffer? Okay, so for those who haven't heard about that, this is a protocol message format from Google designed to minimize the size of the data. It's binary message format. So in that case, using this protocol, you'll be able to configure fast and really low footprint messages between your services and between your browser and server. Just for your information, a few technologies from the front end, we're not going to take a look at them at all, but maybe someone is curious how I'm going to build front end. On the front end side, I'm going to use Phaser. This is kind of convenient way to build some game engine. I'm going to use Project Reactor, of course, because, yeah, the same as before. I will going to use TypeScript because I hate just dynamic typing in browser. This is impossible. That's why I love really typed languages like TypeScript. And of course, we're going to use protocol buffer in order to keep everything in balance and to keep our communication really efficient. So let's take a look a little bit on our source code. I'm welcoming everyone to just scan a link if you are curious what's going on the backend side and you want to look from your phone. So here is the link to the source. And now I'm going to quickly show you what's happening on our backend. Can you recognize what's going on this screen? Can you read it? I will try to increase the size of the screen a little bit. So basically, we have a few modules in our application. So we have metric service, we have game service, server, which is doing basically all the calculation for main logic. So here we have a few things. Okay, here we go. This is a plain Spring Boot application which has 3-tier architecture. Here we have some services, repositories, controllers, of course, configs. On the right hand, you can see plain Spring Boot application. Have you ever done something similar before? everyone have seen this code before, I guess. This is almost standard application. You can go to start.sprint.io and generate the same. All right, this is really plain app. Here we have a few more modules. Ideal is basically our API. This is our generated, and this is kind of shared protobuf API where we have some definition of our DTOs. And here we have some script that generates it, and this is really simple stuff. Our client, which is basically built on top of TypeScript, and our metric service, which does basically or emulates some machine learning. Of course, in this application, in this implementation, I don't want to kind of overwhelm you with lots of code, and I just prepared a few modules that will emulate machine learning, etc. So we have really plain application for metrics collection here as well, which is Spring Boot Up. All right. Let me go back to the slides, and let's go further to analyzing what we can use in order to build our game. Because for now, the most important part is not to understand how to write all the business logic related to Pac-Man game and how we can store the data and blah, blah, blah. This is boring. You can find lots of guides for that. And for us, the most important for today is to understand which protocol is the most efficient for doing communication between browser and server in order to build real-time live game. This is what we are going to understand and build after all. So what we have on the market of the protocols today. First of all, we have HTTP1. This is the simplest one, the common one, and every of you are using this protocol today. Along with HTTP1, we have TCP. This is also really verified by time feature. And along with that, we have cool new HTTP2, which allows us to really efficient, to wire really efficient message sending or something like that. Do we have something else? Probably we have UDP, but it's not reliable and it doesn't work in browser. We have lots of weird transport protocol, which is less possible to demonstrate really easy. That's why we're not going to focus on them. On the other hand, can we use TCP here? Can we use TCP on this browser-server communication? Any idea? I guess no, we can't use it because TCP doesn't support directly on the browsers. That's why we have to use WebSocket. And that's why instead of TCP, we will try to consider WebSocket as a transport for doing communication between browser and server, of course. All right, it seems like the full list of protocols that we can use today without any problems. And how we can start comparing, or how we can do a comparison between them. So I defined a few, from my point of view, important points and characteristic of every application. First of those characteristics is maintainability. So our protocol should be widely supported, the community should be really huge, and we can easily find any answer on common problem at Stack Overflow. This is what we are going to look today. Then, we are looking for a stable protocol, right? For stable transport and for stable solution to our problem. That's why we have to find something that just works and allows us to decrease the number of headache related to development, because we don't want to solve too many problems. Of course, we love them to create another problems, but yeah, less problem, better life for our business. And finally, the most important characteristic should be performance, because we're going to build live application, I remind you again. Okay, let's start with alt HTTP. I'm not going into details about alt HTTP because it's absolutely clear that it has lots of disadvantages, but I would like to just remind you why HTTP is good. Because it's a plain and simple kind of protocol. It widely supported in every browser, and it kind of well known for many years. That's why it's good. So it's simple in development. Spring Framework allows you to just put a few annotations in order to build backend server. That's easy. Then lots of framework, every language, JavaScript, Python, whatever language support, HTTP communication. And one of the kind of benefits is that it's stateless. So it could be better or it could be not, because in order to find out what is the user, we have to, of course, do some actions. On the other hand, the backend logic could be a little bit simpler. So on the other hand, disadvantages of HTTP is, of course, message overhead, because it's kind of it's textual protocol. So you have to send every message in text format, which is, of course, gives you lots of overhead and impact your performance a lot. And that's why HTTP is really slow. Also, it creates almost HTTP 1.1 creates usually a few communications to your server, which that kind of increases a lot on your server because it has to manage a few connections from the browser. Sometimes you have to recreate connections, and it increases also the load on the server, and it's basically inefficient resource usage. Finally, you have what you can only do with HTTP is only request response. Even you have HTTP 2 in the future, maybe HTTP 3, but you still only can do by specification request response. Maybe you can wire server-side streaming or some chunking, but this is hacky way to start streaming from the server to client, but not from client to server. And finally, HTTP doesn't support backpressure. And what I mean it doesn't support backpressure, your backpressure in HTTP looks like that. Yeah, a little bit of weird things happens here, but it looks like that. So you don't have basically backpressure in HTTP. And you have to solve lots of problems with HTTP, like circuit breaker, solving how to handle timeouts, etc., etc. There is no simple way to just live with HTTP. All right. Of course, it's obvious that since HTTP is a little bit not good for our solution, we have to use somewhat WebSocket or HTTP2. Let's focus on WebSocket because this is a common way to send data from the browser to server with high speed. So why WebSocket? Because it's almost the same TCP connection, no overhead happens here, and it designed for high performance communication. Why not WebSocket? Because WebSocket, from my experience, is a little bit complex in development, especially when you start using WebFlux framework or Spring or new Reactive Spring. It doesn't provide you with a common annotation model for handling messages from WebSocket. And in one of my projects, I had the chance to build another application protocol on top of WebSocket, and that was somewhat I want to repeat again. Of course, there is some existing solution and existing protocol built on top of WebSocket, which is, for example, one of them is Sox.js and Stomp, and another one, which is more popular, is Socket.io. So let's try to maybe see what we can build with Socket.io. Again, I'm not going to code right now something related to Socket.io. I'm just going to show you some video from, some recording from game experience with Socket.io. So let's just start playing the game, enter the game, and from the first glance, it looks that everything is good. I can move without any lags, so UI is pretty good. It just works. So what seems like a perfect solution, right? So let's take a little bit more, and let's go further, and let's find my another player. Oh, here we go. It doesn't seem good. Do you think this is good? No, I don't think you suppose this is a really good experience. Oh, what's going on? Some weird things happens, or this is basically the story how Pacman escaped with Socket.io, or could escape with Socket.io, because we are streaming our location, and of course lots of packets for some reason with Socket.io started dropping, and in general I did my best to implement Socket.io server with Java really well, but it's really hard. So, on the other hand, let's try to make some stress tests with Socket.io in order to figure out maybe a Socket.io is suitable for our pipeline, right? Maybe we can use it here at least. So let's try to make some scenario, simple testable scenario for a particular solution, particular framework. And here what we are going to do, instead of using Kafka, we are going to emulate Kafka using, of course, Reactive Streams and code like that. And what's important in this piece of code, this is part of Reactor, the most important here is that the code, the function inside this Lambda will be executed and produce messages only and only when we have some request from downstream. So reactive programming is related to to some flow control, to backpressure control, proper backpressure control. So our subscriber of this stream can say to publisher, hey, give me 5 elements of data. and then publisher have to produce only five elements of data or less, but not more. This is the important. So using such functionality, we can emulate Kafka because Kafka is also Kafka supports backpressure because Kafka has kind of push-pull model. So when you have to consume data, you have to send a request, and then Kafka will return you a few messages, or for example, 100 messages, or as many messages as you requested. So it will be absolutely the same as with Kafka communication. And if we're going to run a test, which will make a load on our app, and the test will be pretty simple. I'm going to show you this test. So let me show you the Socket.io dosser. I call it Socket.io dosser. Where is that? Here we go. Not here. I'm in metric service. So here is the game service. And here we have Socket dosser. So this is really plain app. Here we have some kind of fake matrix generation. This is the same function. And here we have some pipe of creating of n connections to our server, and then making some load using common Socket.io client. So this is basically a convenient way to start sending and making some load, or maybe the simplest way to making some load on Socket.io server. And by doing that, by running this test, of course, we have to emulate all kind of cases on our pipeline. We should emulate some kind of increasement of capacity of our server, and of course, we have to emulate some low-performant endpoint which will slowly consume data. So we have to verify whether the middle server won't be overwhelmed and won't be killed by our producers, and it won't die. And this is kind of the most important in our scenario. So everything will be just working. In order to run everything on my computer, I prepared a few parameters which allows me to minimize kind of the time of running into troubles. And I prepared kind of 1 gig of memory for heap and 1 gig for direct memory, because under the hood, everything is using NETI. So NETI is using some direct of heap, and it's important to have everything equivalent for both of them. And once I run the test and wait for a little, try to increase the size of my endpoint of metric service and then decrease the size of or capacity of my metric service, I will get that. Do you see it? This is basically out of memory. If you're going to look a little bit closer, we will see that we got 1 gig of memory fully consumed. And on the right hand, we will be able to see out of memory. Do you see it? Here, out of memory. This is basically what can happen when we start using Socket.io, because Socket.io is a little bit unstable, I would say. Because first of all, I'm going to share some disadvantages of Socket.io, because when you start writing some server-side code, you have to deal with some JavaScript paradigm, because server-side kind of Socket.io server for JavaScript, for Java was written in the same model and the same kind of paradigm as for JavaScript. So it's kind of unusual way for Java developers to deal with JavaScript-ish code in Java or something like that. On the other hand, average performance, as you have seen from the first demo of Pacman movement, we could notice that latency is somewhat unstable and lots of packages are lost, which is also good. And finally, this is lack of backpressure, because Socket.io is about just server pushing for message pushing. So you can only just push messages, and that's it. You can't control them by saying, OK, give me only 5 messages. And that's somewhat we need in this pipeline. All right, it's clear. For our application, it's important to have backpressure in order to preserve our machine learning pipeline. So what do we have that support backpressure? Do you know maybe something that support backpressure? Any idea? I guess every one of you heard about gRPC. Have you ever heard about gRPC? OK, just a few hands. So this is a protocol from Google again. So it should be really convenient. Google use it for their needs. I'm not sure for which cases they use it. But it should be a really cool protocol. And it's cool because, first of all, It built on top of HTTP2. And as I mentioned, HTTP2 produces only one connection, so it should be really efficient. On the other hand, it provides good development experience. It's well written in Java, it's well written in JS. And finally, it's easy to integrate with protobuf because this is the main API, this is the main format for gRPC, so it's kind of built-in feature here. And you can easily generate gRPC services and API using, of course, a protobuf API and generation. Why not gRPC? One of the important things in our app is browser. And unfortunately, gRPC Web and gRPC Web implementation is really shitty, I would say, because in order to run gRPC Web, we have to install Envoy proxy. This is one of the options. Of course, you can write everything yourself, but this is one of the options, which will talk over with your server over HTTP2, but most likely, between your browser and between your Envoy proxy will be wired only HTTP1 connection, which is the same as with plain HTTP communication. And of course, in order to listen for some stream of data, you have to open some more connection, which is absolutely wasteful, as for me. That's why gRPC Web is somewhat not good. All right, so browser doesn't work as well here. So maybe stress test and our pipeline will handle it very well. So let's take a look. Moreover, gRPC says, gRPC team says that they have backpressure, and gRPC really have backpressure, so let's just verify that. And let's try the test. Let's run the test. This time I'm going to show you some more things. So here we have some kind of my game server. It plays the role of gateway here for sending, propagating data for our pipeline. On the bottom we have running the metric service. Do you see it? So this is a metric service which we are going to kind of control. This is some metrics information, some performance, and here is a kind of panel for controlling backpressure and capacity of our final endpoint and final service. So I'm going to change something to submit request, and as you can see, here we have some, do you see it? Here we have some changes in capacity. I changed that back, and we have some more capacity for our service. Here we have some information about state of our service, and now let's go to our code. Again, the same code as before. Do you see it? Yeah, I'm going to share with you some video because it's really kind of, from my experience, it's really tricky and non-stably to run everything on my machine, but in general, everything similar to our Socket.io source code. And here we are going to send some messages to our client. So basically it's the same DDoS code as before. Now we are going to run it, wait a little bit in order to see whether the new connection is coming. So it's running. Yeah, we can see new connection coming. And now we are going to change the capacity of our service, I guess. Or we have already changed that. Yeah, we have already changed that. So as we can see, the state of the service is pretty stable. Nothing happens, so it just works. In a few minutes, we will observe, in a few seconds, we will observe the results of measuring performance. So performance is pretty well with gRPC. 150K messages per second. It's a lot of messages per second just for my machine. And now let's try to decrease the capacity of our machine to minimum, to 100 of elements per user or per channel, per doser. And let's see what's happened. So we can see that there is no messages, there is no capacity to ask from our kind of producers. And now let's take a look at what happens. So it seems that backpressure works. The results on the graphics is almost identical, do you see? So it shows that we decrease in performance, we decrease in number of messages that we produce, which is fine. But wait, what's happening? Do you see it? The memory kind of usage increases. Well, this is somewhat not okay. So let's see. We reached the maximum of our available memory. And that's somewhat we don't want to see in our application, in our pipeline, in production especially, right? Because in production, of course, we don't have, like in this case, we just ran only 200 users or 200 producers. In reality, we have much more producers, and only 200 of producers cause it out of memory in this pipeline. So yeah, let's just stop it And let's just back to our kind of presentation in order to figure out what's happened. If you're going to take a look at our graphs again, it will be obvious that at the beginning, we had the same kind of throughput on both sides. We have the same throughput on our gateway or middleware server, and we had the same throughput on metric server. This is fine, so it just works. But then what happened? When we decreased immediately or suddenly decreased the capacity of our server, of course, backpressure started a little bit working, but as you can see, game server produced much more messages in comparison to consumption of metric service, where metric service consumed only, for example, 75K of messages, game server produced at the same moment 100 or 100K messages, which is 25K messages should be stored somewhere, which is a problem. And of course, at the next moment, we had the same picture. So that's why, because some of the messages should be stored somewhere, and they were stored in the direct memory because it's a netty under the hood, we got this picture, and after all, we got this out of memory. Because in general, backpressure of gRPC happens only between one server and one server. There is no kind of full backpressure pipeline or full control of backpressure between the endpoint and between the producers. That's why gRPC can somehow control over TCP backpressure message sending, but when it comes to suddenly kind of decreasement of performance of endpoint, the middleware and producers doesn't know anything about that. And this is a real problem with gRPC because it doesn't have real backpressure. Doesn't have end-to-end backpressure on your pipeline. And in your life, you will have lots of services connected in one chain, because this is kind of real business and how we build microservices today. All right, so it seems that, yeah, backpressure there is, but not as we want. And you can believe me, because I did as much as I can, as much as I can, in order to contribute to reactive gRPC wrapper. We used everything reactive here, and I ensured that everything is implemented correct, working correctly, re-implemented everything related to correct implementation of reactive streams and communication in that way. That's why I'm pretty sure the test was run really correctly with gRPC. And our result for gRPC as well, kind of similar to Socket.io, unfortunately. However, gRPC has its own advantages because it has good performance, it has simplicity in development, it has wide support. gRPC could be used in any languages. I care that I should share kind of good points about gRPC because not all cases in reality requires to have some piping, etc. So for some cases, gRPC will be really good. That's why I have to say some strong sides of this framework. And of course, efficient resource usage because of HTTP2, so just one connection. However, from the disadvantageous side, we have unclear API because we have to use another wrapper for reactive programming. gRPC does not provide with Reactive Streams standard API. Also, there is no real backpressure. There is some backpressure, but not real, that we want to have for our case. And this is just a wrapper on top of HTTP, so there is no smart application protocol as we wanted. And finally, gRPC web is somewhat really bad. And yeah, no more words about that. So in general, what we can summarize from what we saw in the previous slides is everything either slow, hard to work with, or unstable. And for some cases, there is some lack for browser, etc. And in general, do we want to solve all this problem in production? Or we just want to use something that provides us everything at once? The same was 3 years ago at Netflix, because they decided to use gRPC for their gateway, and that was demonstrated actually as a case of Netflix where they observed the crash of gateway when on their chain, while the load of and performance of different chains and different services in the chain changed over the time, and that's what happened with their gateway. And you can find some interview with one of the developers from Netflix that kind of explain what happened with their use cases and what was their case studies with gRPC. So after all, they decided, so since everything is really bad, let's try to create something new. And what they did, they created a protocol. And that protocol got a name RSocket. So now we're going to take a look at RSocket. And now in order to not waste your time, to preserve your time, I'm just going to run the same identical test. So what here we have? Here we have the same game service. So do you see these comments? I'm going to enlarge it. The same comments as for previous cases. So I'm just going to run this service, this game server with the same parameters to make sure that everything is kind of fair. Then I'm going to run metric service, and I'm going to connect my visual VM to what's happened. As usual, demo gods. Port 30 already in use. What else could I got? So I have to quickly kill off all of my Java apps in order to, let's kill it, and let's do just a sec. Let's kill this Java, and let's kill this Java. Yeah, I hope it will work right now, after all. So ensure that now we don't have any Java apps running the same, and now we will be able to see, yeah, let's close this guy. Yeah, no, it's not running. Why? What's happened, buddy? Okay, let me just try to run it from here. Oh, those demo gods. So in general, why it's running, I'm going to quickly introduce what is RSocket and why should we care about RSocket. In general, RSocket is a white side. That's why I like it. And first of all, RSocket is a binary protocol. So similar to gRPC, it creates only one connection between your client and server and sends data in a binary format, which means that it's really efficient. But however, on the other hand, you have to care about decoding and encoding of all of your messages. Then, what else do we have here? We have multiplexing. So this is built-in feature, and if you want to send lots of streams, it's built in RSocket. It provides for you logical streaming and supply to every logical stream some internal ID and send this internal ID over the network so the receiver or recipient can figure out to which kind of stream, logical stream, I should route this message, this frame. What you have to do with RSocket, for example, this RSocket Java, you have to just use Project Reactor, enjoy reactive programming model, and that's it. Everything is done under the hood by implementation. This is cool. It's bidirectional. What it means? At the first stage, you have to just connect to your server or observer, and then both the connector and the kind of receiver are peers, and they both can send messages and request some data from each other. So both can implement some handling logic and provide some response to each other, which is also cool. So it's peer-to-peer communication. In turn, it has real backpressure because this is actually implementation of reactive streams. At Netflix, they care about reactive programming. They cared about reactive streams because they supported RxJava. They supported everything was written in Netflix using reactive programming. I'm pretty sure that lots of services are still running using RxJava. So they cared about reactive streams model, and that's why they provided a reactive streams implementation of the protocol. So when you say, I want 11 elements, it can convert it to frame, sends to recipient, then recipient decode it. This is everything built in, and then send only 11 messages and not more. This is important. Finally, it has few interaction model. It's not only about streaming. RSocket is not only about streaming. It's about normal communication. So there is request response, and you can do plain request response as you have done before. It allows you to say fire and forget, which is efficient request response. So you can send messages and all kind of immediately close the connection because you don't want to wait for response. There is request stream, so you can request for some streaming data, which is also cool. or there is some stream case when you can send stream of messages and you can receive some stream of messages back. So all of these communication models are built in. And another notable features that could simplify your life is leasing. So just imagine, have you ever used circuit breaker in your project? So a few hands. The circuit breaker requires you to set up, first of all, some timeouts, to set up some retry logic, etc., etc. And you basically don't know how to, for some cases, you have to create somewhat distributed circuit breaker because you have to coordinate a few services to not overwhelm, for example, another one. And this is a problem. In RSocket, we created a feature called leasing. So when you connect to the server say to you how many messages or requests can you send or can you create to him. And in this way, it preserves kind of its capacity and stability because the server knows how many requests in general it can handle. And that's why it can say to this connection, you can send me 10 requests per second and not more. And then the sender will require, or will be mandated to send only 10 requests per second. Another feature is resumability required then at Facebook, because also Facebook joined to support of RSocket. And they, for their needs, for their kind of server mobile communication, they required resumability in order, just imagine, you're walking through the street, and you connect it to one Wi-Fi, and then you connect it to another Wi-Fi, and your connection basically is lost, which means you lose all of the data the server sent to you, and that's a problem. This resumability, you can just reconnect using another, for example, Wi-Fi or network, and then the server will figure out, based on the provided session ID, which stream was sent to you before and will continue sending all of those data. And this is cool. You don't have to implement with RSocket yourself that. And finally, there is fragmentation. So in case you decided to say send gigabytes of data over your messages, you can easily split them on some small fragments. Yeah, let's take a look while it's running. I'm encourage you to scan this link because now we are going to play in some real game, some real Pac-Man, and we will try to kind of try to understand whether implementation of Pac-Man game using RSocket is good enough. During this time, I'm going to take a look what's happening with my server. So still the same sheet. That's not good. All right, I'm not going to focus on that this time. For those who are curious, I'm going to show this afterwards on the backstage. But for now, what I want to share with you is, of course, I want to open the browser and ensure that you can enjoy the proper real-time multiplayer Pac-Man game. So let's just open Dynaman link. And yeah, it could take a little of your network to download everything. And what you have to do on your phones, of course, you have to open everything from Chrome browser because, yeah, I'm shitty JavaScript developer. That's why Mozilla doesn't support this game. But in general, you should enjoy the playing. This is almost real-time game. Yeah, a little bit of flux, but yeah, you can see that it works. So let's try to find someone. Yeah, great. So a little bit of flux because the small machine is provided. Oh, we got some Pac-Man. Let's try to eat it. Great. So it works, which is good. A little bit of flux. So let's try to figure out how we can use RSocket on the daily basis. Now I'm going to show you a few kind of simple steps to start working with RSocket Java and explain what you can do when you're back home. For example, for that purpose, I switch it to another branch. And now let me open the main app and try to explain a few things to you. So in order to start using RSocket Java, since we're Java developer, you have to bring two dependencies. RSocket core, which brings all basic kind of implementation. And since RSocket is kind of language agnostic solution, so you can use it in any language on top of, for example, in JavaScript, in Java, and you can run it on top of any transport like TCP or WebSocket. You have to specify as an additional model which transport implementation should be used here. So here we use native implementation of the transport. And now let me quickly write some code in Java in order to show you how it works. So to work with RSocket Java, you have to start with, oh, it's indexing. Come on. The whole demo gods decided to punish me this time. What's happening? All right, at least I will try to play the game. Maybe this will work. OK, so let me go back to the slides then. Since nothing is working related to the demo, shit happens, I'm going to share you a little bit of advantages of RSocket. First of all, this is simplicity in development. Let me just quickly then show you what you can do with afterwards, after kind of when everything will be done for you, what you can do with RSocket. So basically, what you have to do with RSocket, what's going on? Come on. What you have to do with RSocket is basically use RSocket RPC, which is implementation of RSocket with RPC communication model. And basically, in order to use the same kind of gRPC communication model and the same protocol buffer as a message format, you have to bring to your application one more dependencies. You have to bring to your application RSocket RPC. So here we go. Here we have RSocket RPC. And RSocket RPC will bring you everything related to message routing and kind of message encoding and decoding, which is cool. So then you have the same generated code as before as with gRPC. So here we have some RSocket RPC generated code, which is basically a really beautiful code based on top of Project Reactor, which is cool. So all you have to do then afterwards, after usage of this stuff, you have to implement some few controllers on your business logic, on your controller side, like that. Of course, you have to use Project Reactor here or another reactive libraries because everything is Reactive Streams. But in general, the implementation will be really simply. And finally, what you have to do after all, you have to implement a few configurations in order to supply your business logic to the generated code like this. So you have to auto-wire your kind of implementation of the service, create some server or handler for all incoming RSocket messages, and then create some request handling RSocket, which is basically a representation of RSocket in Java, which allows you to do all this kind of communications that I mentioned. So here we can see request response, request stream at any other communication model. For example, this is stream-stream communication model in RSocket. All right, we are running out of time, so let's just do a quick summary. In general, advantages of RSocket is simplicity in development, it's high performance. If we would able to run this, we would see maybe 200 and 250K of messages per second, which is high performance and higher than gRPC provides us. RSocket is about efficient resource usage because only one connection is wired. Wide communication model, we have seen all type of communications that we could ever need in real development. And of course, this is high flexibility in setup because all languages also supports RSocket. So disadvantages is not widely supported for now because the community for now is shitty. Nobody knows about RSocket. That's why it's a big problem. And what you have to do right after that, you have to Google for RSocket, go to GitHub repository and maybe put a star here. Please do that afterwards. Finally, RSocket is still under development. It's in 0.x version, so it's still under development. Lots of things could be changed, lots of bugs still in place, so it's a kind of in-progress project. In general, yeah, here is GitHub repository. In general, main maintainers of RSocket is Facebook for now. It's natified, it's my company, it's pivotal, so you can find implementation of sprint messages and integration of sprint messages with RSocket. And not that far to us, to our team joined Alibaba, and they planning to use and adopt RSocket a lot as well in their ecosystem. Finally, this is the summary table, final table of all protocols. In general, every protocol has its own benefits. For plain communication in JavaScript, for building some JavaScript-only communication, of course, Socket.io will be the best because it's designed for JavaScript ecosystem. For better resilience, because Reactive-System and Reactive Streams is about resilient and resilient communication between microservices, you would probably need RSocket because this is an amazing solution, and this is basically the solution designed for preserving your stability and providing you basically performance the same as with gRPC, for example. Finally, a few more resources and links that I can share with you. First of all, there is community, RSocket community, so if you have any questions, please ask them here. We have video channel related to RSocket, so please visit here to watch a few more kind of motivation videos related to RSocket. And here is the first commit to RSocket sprint, so soon you will see fully fledged kind of with all future implementation of sprint messages, sprint messaging on top of RSocket as well. And here is what we are doing. We are doing some enterprise solution for RSocket. We are building message broker on top of RSocket protocol. So if you want to use some enterprise solution ready to production today, please visit that link and try to assess our technologies. Also, if you want to learn more about RSocket, follow me on Twitter, follow my company on Twitter, and if you have any other question, please ask me. And thank you for your attention.
Big applause to Oleh. Nice, cool stuff, Oleh. Well, we have no time for questions because we need to keep the scheduling with the other room, but I'm pretty sure that Oleh will answer any question in the backstage.
Absolutely.
So big applause to him again, please.